Have you ever wished that you could be in two places at the same time? Well, thanks to quantum mechanics, now you can. Well, sort of. This is an electron. We observe it at a specific position at a specific time. But what if I told you that this electron can be here, here, and here all at the same time? Still not convinced? Let's dig a little deeper. Particles such as electrons have distinct wave-like properties. This means that they can be both represented as individual particles and waves. This wave behavior displayed by an electron can be represented by what's called a wave function. But what exactly is the wave function? Let's look at this conceptually. This glass box contains an electron. When it is not covered, we observe it with full certainty at a specific position as an individual particle. But when the electron is covered by the cloth, its position is uncertain. This means that there is a certain probability of the electron existing in different locations inside the box. Until it is observed, the electron exists in all of these states at the same time. This is called superposition. If this wave function were to be graphed, it would show the probability distribution of the electron being at a certain location, known as the wave function. Wait, so if an electron can have a superposition, I can too, right? Not exactly. You see, humans have a lot more mass than electrons, and because of this, the wavelength of a human is so small that a human would not be able to exhibit wave-like properties like an electron would. Although the electron's position is uncertain, it is known that it lies inside the box, so it has a 0% chance of being outside the box. At a quantum scale, this would mean that only certain frequencies of the electron's wave function would be possible. If only certain frequencies are allowed for a wave function, the electron is only allowed to be in certain states of energy. To obtain these energy states in an electron, a scientist by the name of Erwin Schrödinger created a mathematical wave equation known as the Schrödinger equation. I'm not going to bore you with the math calculations because believe me, you will fall asleep. But this is the equation in its simplest form. The Hamiltonian is a set of mathematical operations that operate on the wave function. When operated on the wave function, it produces the corresponding energy states known as eigenvalues. Why is this even important, you may ask? Well, without the Schrödinger equation, there would be no quantum mechanics. The movement of subatomic particles could not truly be modeled by existing concepts. From the most advanced supercapacitors to even basic electron motion, the Schrödinger equation explains why classical physics cannot be applied at a quantum level. So, if you ever wanted to be in different places at the same time, all you have to do is shrink yourself to the size of an electron, and who knows, it might just happen.